Great. So I want to talk about ZFS course. So who in the room has run ZFS in the last year? In the last 3 years, say? Who here was running it back in 2005? Okay, great, a couple hands. And earlier in 2005? Okay. So ZFS started as a project properly inside of Sun to reinvent storage in about 2001. In 2005, with the initial release as part of the Solaris 10 update and part of Open Solaris. And the vision, of course, was to create enterprise-class storage out of these commodity components, to take all of the intelligence we've been built into RAID controllers and to smarter disks and to smarter storage arrays, and bring that up to the level of the operating system, to the level of the file system. Further to its design, pouring out 20 years of operating systems and file systems history, and instead building a completely new model for management. It's designed for incredible scale, performance, et cetera. So designed to be a truly new model for storage for the 21st century. So in 2005, when it was released, enterprise class storage, the kind of thing that you would buy from a NetApp or an ENC, or you actually pay real money for, consisted of 15K RPM, either FC, Fibre Channel, or SAS drives, and it had NVRAM as a write accelerator. Now, ZFS around that time was targeting kind of that same market, but doing so with 7,200 RPM drives and no NVRAM. And as this gentleman in the back, who had been running ZFS for the last 4 years, can attest, the performance of ZFS kind of sucked then. And the problem was not ZFS in itself. ZFS was correctly designed to take advantage of these performance characteristics. The problem was the commodity components that we were trying to build it on top of kind of weren't performing as well as those enterprise-grade components. So just as an aside, we were relying on those 7,200 RPM drives to deliver a lot of different aspects of the system. Capacity, throughput, that's megabytes per second, read IOPS, write IOPS, everything was dependent on those 7,200 RPM drives. And not surprisingly, the 15K RPM drives were faster. Now, ZFS allowed you to build something that was much cheaper, much larger scale, but the performance kind of wasn't quite there. But kind of lucky for ZFS and lucky for the industry, there was this new innovation or I should say, an old innovation that was kind of made new again in Flash. So Flash is, I correct myself, it isn't new. It was designed in the early 80s. But the thing that's been interesting about Flash is that its recent rise to relevance becomes of its economics. So I assume everyone here is fairly familiar with flash memory. It's a non-volatile technology. It's very fast. It's fast for writes, about 200 to 300 microseconds, depending on exactly what flash you're talking about. But it's very, very fast for reads, about 50 microseconds for a 4K read. Now this is compared with 7,200 RPM drives, which have latencies in the neighborhood of low teens milliseconds, versus 15K RPM drives, which have latencies, 8 to 10 milliseconds in that neighborhood. So now, about 2001, when ZFS was being designed and conceived and built, Flash was very much off the radar. It cost about as much as DRAM, so there was very little to be gained there. It was kind of a novelty device for embedded systems and for systems designed by the military that had to live in helicopters and things of that nature. But in the past year, it's now a tenth of the cost of DRAM. Now, it's still much more expensive than disk. So while some people are proposing to replace disks entirely with flash, I think that for the vast majority of deployments, the vast majority of applications, that's not going to be economically tenable, just because disks are so much cheaper and the price of disk continues to drop. So what we want to do instead is not replace any particular layer of that storage hierarchy, but augment it to complement that hierarchy of disk to DRAM with a new tier. So what we have here is a graph of the price performance of flash versus other technologies such as DRAM and 15K RPM drives. And we can see that flash actually sits, this graph kind of got mangled, I'm not really sure how, but SSDs, or pardon me, flash, sits right in between DRAM and drives in terms of both the latency for a given operation and also the dollars per gigabyte. And while those trends are, the exact position of this graph is kind of changing, the trends are such that Flash is still sitting right nicely in between those, and unlikely to cross either of those in the next 10 years or so. So what we have is a completely new tier in terms of economics, in terms of price per performance for these storage systems. So ZFS, now in 2008, built a couple of key technologies that we're using to enable what we call the hybrid storage pool. So on one hand, we have the ZIL slogs. So this is, I don't know if any of you were in Ben Rockwell's talk just now, but he was talking about ZFS performance tuning, and one of the key areas here is the ZIL, the ZFS intent log, where synchronous writes are allocated, so we don't need to block on the speed of the spindles. And Neil Perrin did this work in OpenSolaris and did an excellent job there. So that's on the write side. On the read side, ZFS already has a technology called the adaptive replacement cache, the ARC. And the ARC is responsible for managing DRAM and managing this cache so that when reads come in, they can be serviced very, very quickly out of the ARC, out of that DRAM cache. Now, something that I conceived with Brendan Gregg is the L2 ARC, a second level adaptive replacement cache. The idea here is to build a much larger cache, larger than DRAM, to be able to accommodate your working set, and have that cache be able to hold an entire working set, which presumably is smaller than your total data set. So both of these are, of course, available in OpenSolaris today. So when we're talking about these different kinds of devices, or these different kinds of technologies, we must ask the question, what sort of device do you want to fill these different slots? What kind of device do you want for a ZIL slog device, and what kind of device do you want for this L2R? So, and these are very different kind of requirements. On the ZIL side, we're only ever writing to the ZIL. The only time you read from the ZIL is when you lose power or there's an unexpected system interruption and we need to replay the intent log. Otherwise, it's basically a write-only device. And what you really care about there is the latency. You really want those synchronous writes to be acknowledged very quickly and written back. The capacity doesn't matter a huge amount. We tend to be able to flush things out to disk very quickly. So 5, 10, 15 gigabytes is more than adequate for that kind of device. Now on the flip side, the L2 ARC device needs to be very, very fast for reads, but it doesn't really matter so much for writes. Writes just have to be non-pathological and not interfere with reads. And then it also needs to be high capacity. The idea is that you want to cache your entire working set inside the L2 ARC. So you need enough capacity out of these devices in order to do that. Further, it needs to be economical to do so, so dollars per gigabyte really matters for the L2 ARC device. So what we have in 2008 is what we've seen is an explosion of SSDs. Now, have people here evaluated SSDs, played with them? Anyone? All right, great, a couple of hands. So SSDs are very much becoming relevant when you see the W and buy SSDs very easily. But they're really designed not as ARC devices or ZIL devices, but instead replacements for hard drives, and many of them replacements for your laptop hard drive. So they're pretty good as a ZIL device, and they're pretty good as an L2 ARC device, but they're not really ideal. So for example, you get the Intel X25E. This is a device you can go on CDW, buy for about $500, and it's actually a terrific device. I mean, I would definitely put it in my laptop if I only had 32 gigs of stuff to store. It has great rate IOPS, about 3,000, which is a couple orders of magnitude than what a disk can do. 35,000 read IOPS, which is way, way more than your disk can do. And the dollars per gigabyte is terrific. But the problem is, for a ZIL slog device, we'd really like more write IOPS. We can do a lot better there. And on the L2 ARC side, 32 gigabytes is quite small, and even packing a system full of them, it's hard to get enough in there to really build an adequate device. So what we're going to see, I think, in 2009 is SSDs which are better suited for these two use cases. But nevertheless, we took that device in particular and designed a hybrid storage pool to sort of benchmark it and give a sense of what can be done with this. Now, in this particular example, we did this in early 2008. We presented this at the Intel Developer Forum. So we took the Intel SSDs and one of our CPUs, or one of our servers with Intel CPUs in it. running Open Solaris and ZFS, of course. And on the left-hand side, we put together kind of the gas guzzler, conventional Hummer H3 storage pool with 10K RPM SAS disks. And on the right side, we have the hybrid storage pool with our 400 gigabyte, 4200 RPM SATA disks, and then one SSD for a ZIL device and another as an L2ARC device. And here are the results we got. So again, the hybrid storage pool is in blue, and the traditional storage pool is in this kind of orange color. And we can see, looking at the similarities, first the cost is about the same. We're about 4% more with the hybrid storage pool, but effectively it's about the same. The write IOPS, we have a teeny bit more, about 10% more. But then you look at some of these areas where we have real disparity. For example, on the read IOPS, we have 300% more, right? 300% of that total. So we're doing quite a bit better than the conventional storage pool. Similarly with power, with these SSDs and these slower RPM disks, we're doing much better in the total amount of power we're consuming, and we produce twice the capacity, so you have twice the usable capacity of the storage pool. Now, for each one of these comparisons, you could tune the hybrid storage pool however you like. So for example, if we only wanted to meet the read IOPS and meet the capacity, we could then bring our cost down significantly, and sort of you can play that same game however you like here. The key observation here is that the hybrid storage pool divorces all of those aspects of the storage pool, that is to say, capacity, throughput, write IOPS, read IOPS, and instead splits them out into different components, where you're getting the best economics for each of each of those components and having each one play to its real strength. So now on the 7410, which is the Sun Storage 7410 is kind of our expandable, clusterable storage server that Sun announced back in November, and this is the product that I've been working on for the last couple of years. So now we looked at the SSDs that were available in the market, and we were kind of looking for something that would do better. We talked to these SSD vendors and tell them we wanted an SSD that we wrote to and we never read from. Why would you want that? And then we told them we want one that you read from very quickly, but writes kind of could take whenever, and we didn't really care about the quality too much. So this was very much outside of the domain that the SSD vendors were considering. Instead, they were really focused on replacements for hard drives, replacements for laptop hard drives in particular. Well, we worked with a couple of vendors and came up with, we have two different SSDs that we use in the 7410. And the two are for the ZIL device. We have what we call LogZilla. It does about 10,000 writes per second, so that's about 3 or 4 times more than what we get out of that Intel device. And of course, it scales. So as you need more write IOPS, you can get more LogZilla devices. On the other side, for the L2ARC device, we have what we call ReadZilla. It does about 20,000 read IOPS, and each one is about 100 gigabytes. We can scale that up to 600 gigabytes. So it can cache a full 600 gigabyte working set on the head unit, and that provides latency then of about 50 microseconds, whereas going to disk would take multiple milliseconds, tens of milliseconds. So here's just some of the results. Now, I think I've heard allusions in a couple of different talks to the analytics feature that's built into the Sun Storage 7000 series. But this is a snapshot from that box that I pulled off a colleague of mine's blog, Brendan Gray, who again was responsible for writing the L2ARC. So we can see the graph kind of divides into the middle. Now, on these top two graphs, what we're looking at is the latency of a given operation. And the darker the band is, the sort of more samples there are in that location. The scale on that top graph is, on the top two graphs, is 10 milliseconds. So you can see on the left is when we have the L2ARC disabled, and on the right is when we have the L2ARC enabled. So on the left, you can see every operation is taking on the order of a couple of milliseconds in order to satisfy those requests. And we have a big empty band in that several millisecond area, because that's just kind of the speed of light for a hard drive. Now, on the right side, we then have a very dark band where we see ops being served, or serviced rather, by the L2ARC devices, by that ReadZilla device. Now, on this graph below, we see the total read IOPS to this hybrid storage pool. Again, on the left, disabled, on the right, L2ARC enabled. And so we get about a 500% increase by enabling the L2R and by using that, and that's an IOPS increase. Take the inverse of that and you get the average latency for an operation. You see the L2R has a huge impact on read performance, and the hybrid storage pool will help both on reads and on writes. So again, that traditional storage pool, just to hammer home this point, takes the hard drive and relies on it for all aspects of performance capacity. The HSP, the hybrid storage pool, breaks that apart. So disks are hard to beat in terms of capacity, and they're hard to beat in terms of throughput. Now, SSDs do have terrific throughput, but at a much higher cost. When you take an equal amount, take a fixed amount of dollars and buy SSDs and buy disks, you're going to have more throughput with the disks. It's just hard to beat 100 3.5-inch disks, even spinning at 72-inch RPM. And we have read-optimized flash for our read IOPS, and then write-optimized flash for our write IOPS. Now, we can scale on any of these dimensions to suit the application. So if you have an application that needs tons of read IOPS, then you buy more read Zilla devices. If you have an application which exhausts your write IOPS, you get more intent log devices. So with traditional storage pools, to some degree, the answer to your performance problem is rather simple. Buy more 15K RPM drives. But that's a very uneconomical way of spending your money, and you're buying aspects of those drives that you really don't use. You see performance rigs that people set up where you have tons and tons of 15K RPM drives, and you're just using a sliver of that capacity. You're just using those 15K RPM drives for their ops. So this is a way of getting that much more explicitly. So now, how do you actually do this with the ZFS? So there are kind of two categories here. One is when you create your Z pool, you can add log devices using the keyword log, and cache devices using the keyword cache. Or if you've already built a pool and you want to add devices after the fact, you do Z pool add cache, and then your cache device, and then Z pool add log, and then your log device. So as I said, the SSDs that you can get today off of CDW or wherever are really fine to start doing these tests and evaluating performance and see what kind of performance you can get out of ZFS with the hybrid storage pool. I think in 2009 we're going to be seeing a bunch of products both from Sun and from the industry at large, which are better suited for the bigger capacity for the L2R and faster for Zilla devices. Just kind of wrap it up here. The hybrid storage pool is enabled by ZFS, and those decisions that were made in 2001 to 2005 that built ZFS were really validated by how easy it was to adapt ZFS to use Flash and to integrate Flash into that storage hierarchy. Oh, there we go. Just want to have everyone see if everyone's paying attention. So it allows us to make optimal use of every resource in the system, from DRAM to Flash to disk, and really build the most economical system. A lot of other vendors are looking at Flash, again, as a replacement, and we've taken a different approach in ZFS, in Open Solaris, where we're using Flash seamlessly in the system and integrating it in a way that doesn't require explicit management and doesn't require people to even be aware that there's Flash under the hood. Further, just sort of casting the view out to 2009, today we're using, there's kind of two different kinds of Flash, SLC and MLC. And SLC is very much regarded as kind of server class, MLC as consumer grade. If you have an iPhone, that's MLC. If you have a 7410, everything in there is SLC today. We're looking to use the L2R. I should back up. The economics of those two are about a factor of 5 off. I think raw MLC costs about $1.50 per gigabyte today, whereas SLC is about $5 a gigabyte today. So we really want to start moving towards that MLC trend as much as we can. There's certainly reliability aspects of MLC which makes that difficult, but with the L2R coding system, which is very well suited to take advantage of that, where an error from the L2R could just be satisfied by the main storage pool and it won't cause any other problems. So we're really looking to move in that direction. And we're looking for SSDs that are really designed explicitly for the hybrid storage pool in 2009. You can kind of think of this as hierarchical storage management, but without that management component. So just seamless integration, and that's what we have in ZFS today. All right, so thanks very much, and I hope there's some questions.
I just have a question about the interconnects used, both the ReadZilla and the WriteZilla are both SAS attached, correct?
Correct. So, well, that's actually not correct. So we use, for the ReadZilla, we use SATA. Both of those devices are SATA devices. For the ReadZilla, in the 7410 at least, we attach it right to the MCP55, which is on the controller's motherboard. And then for the LogZilla device, we attach that over a SAS HBA, so it's sitting in a SAS GUI.
Okay, so my question is, both SAS and SATA are both interconnect technologies that are targeted towards spindle-based storage, or they were designed initially for that. Do you see in the future the flash-based storage moving to a different interconnect that uses semantics that are more specific to flash as the backend store?
That's a great question. And I really see SSDs today, flash SSDs in particular, as kind of analogous to the way I hook up my iPod to my car stereo, which is like with a tape adapter. I don't know if anyone else has it. Right? It's like, I have like my power adapter is my cigarette lighter. My car doesn't even come with a cigarette lighter. It's called a power port, right? A big power port, a big rectangular audio in. And I mean, that's kind of like an anachronism from kind of how those technologies became adopted, right? It's like your iPod, to some degree, became popular because it was backward compatible to some degree. Now, when you get your Toyota Prius or whatever, it comes with an 8-inch port, so you plug your iPod right in or whatever. I think that in much the same way, you're going to see the same thing with SSDs. SSDs today are connecting through that tape adapter of the 3.5-inch drive slot or whatever. In the future, we're going to see it both migrate to other areas of the system where it makes more sense. Now, there's some aspects of living in the JBOD which are attractive and I think are unlikely to change. But there are other aspects that I think would gain from getting on the motherboard, getting on the PCI bus, and someone's exploring a bunch of those different options.
Okay, and the follow-up to that is there seems to be a little bit of debate. Recently, Linus Torvalds was saying that he wanted to see SSDs be like a data object storage where it's just agnostic of the system, the OS doesn't need to know anything about it. And then the other side of that are people saying that SSDs need to be basically dumber, and that the OS needs to have a greater visibility inside it so they can manage the chips directly, manage wear leveling, be aware of the layout and the partitioning of different cells and whatnot. What side of that argument would you come down on, and where can we expect maybe Sun's development to be concentrated on in the future?
Well, I can't speak for Sun at large, but I think that my personal view is towards the latter end of that. That is to say, I think that the analogy here is the way ZFS operated with disks. So ZFS saw what was happening. We saw what was happening in RAID controllers and smarter disks, where disks where there's like disk level encryption, and I think we were in compression and things of that nature. And we're taking all of the intelligence that was sitting in the RAID controller, sitting in the disk, and pulling it back into the operating system, file system, hardware, or software, pardon me. And there are real advantages to that because from that level, from the level of ZFS, you have a much more global view, so you can make better decisions. As you say, these SSDs are actually fairly complex devices, and part of the reason they're fairly complex is that they're trying to act as straight replacements for hard drives. They view their target, i.e. Windows, as an immutable entity, right? It's like you have to build something which works out of the box with Windows. That's the requirement. Sun obviously doesn't have that requirement for a vast majority of what we're doing, especially with our closed storage appliances. So in those cases, I think that where it makes sense economically, we would like to take some of the intelligence that is living on those SSDs and bring it to the level of ZFS. Of course, all of these arguments are economic arguments, right? So if we don't have the volume with things like one camp of Linux wants to do and like we want to do with our hybrid storage pool, it's never going to make sense for us to disable wear leveling and to make devices that are that dumb. So we need, regardless of what happens, we need the economics are going to win and volume is going to win. But where I'm going to push it, and where I think Sun is going to push it, at least in our appliances, is toward that latter argument, towards dumber devices where the software does more.
My question has to do with the performance benchmark results that you shared. Were they done for a real-life workload, or was it a synthetic benchmark?
Specifically, this is the workload that we demonstrated at IDF for that second workload with the pre-graphs.
The second one.
Let me just back up there. That was a synthetic benchmark, but one that was designed around the workload, the particular customer. You know, part of the reason why I don't have a real workload here is because you know, while customers have deployed this, I don't happen to have their analytics data, and to many of them, they would view that as proprietary. But I think in the next month or two, we'll be seeing many more disclosures from customers of the Sun 74, 7410 and 7000 series in general, coming public with results that they've seen with the hybrid storage. And then again, using graphs like this to advise future decisions to decide, I now need another read tool, I need another log tool. So.
Okay, so we can look forward to more information on real-life workloads and what worked well, what didn't work well.
That's right. I mean, you know, we get as much real data as we can provide, but again, a lot of this is viewed as proprietary information by the companies that generate it.
I have a question from the webcast. Hope it makes sense. What happens with iSCSI and the HSM with 7410?
Okay, I'm going to interpret that as what happens with the iSCSI with the hybrid storage pool of the 7410. Is that, so whoever is listening on the webcast can correct me if that's not right answer. With ZFS, whether you're operating over local storage, NFS, CIFS, WebDAV, FTP, whatever, or iSCSI fiber channel using Comstar, everything goes through the ZFS DMU. Everything goes through the ZFS ARC, L2R, ZIL, SPA. So this is at a much lower level in the stack than at the protocol. So all of this applies to both file-based protocols and block-based protocols.